Before I start with my official intro, I've just got to do a shout out to the student in Mr. Kansas class who grew for that entire intro. So thanks, dude. That's awesome. My name is Jesse. I'm here with Exploring by the Seat of Your Pants. And if you're joining us for the first time, like so many of you are today, we are all about bringing conservation, adventure, and science into classrooms around the world. Now, you are catching us on our epic Space Month. We have had NASA engineers, roboticists, explorers of all kinds all month long. Every program we do is on our YouTube channel. So if you want to check out programs with Abby Freeman, Aaron Yazzie, Ravi Prakash, Ashwin Vasvada, and more, they are all right there, plus like hundreds of others over our 10 years doing amazing space programs. So please do check that out. Now, before I introduce today's speaker, I want to highlight we will have a Kahoot today. Now, I don't have the game pin just yet, but I'll bring that up in the middle of the broadcast. But if you want to play along with a little 4-question quiz between the talk and Q&A, get ready for that, kahoot.it. Stay tuned for the game pin in the chat throughout the program. Now, today, I'm really excited because we've been talking about Mars a lot this month. We talked about Europa this month. There's a lot of cool stuff happening in the space field nowadays. But what we haven't talked about is journeying to an asteroid, which is super, super cool. So we're going to learn a little bit about that today from Paige Arthur. She's coming in to talk to us about Psyche. So we're going to learn about a whole new mission. I'm going to learn a lot about this mission too, because I don't know that much. So I'm as excited as you guys are. And so without further ado, I'm going to zip it. Paige, welcome to the broadcast. Thanks so much for being keen on exploring by the seat of your pants, and take us away.
Thanks, Jesse. Super excited to be here. All right, I'm going to share my slides with you guys.
While you're pulling them up too, I'm going to highlight jpl.nasa.gov, which Paige gets to be a part of, which is like the most storied research facility in the world ever. They're so neat. And I will follow up with a cool link to all sorts of cool educational resources, including loads from them. But Paige, you're in. It looks great. Take us away. I'm going to disappear again. Thank you so much.
All right. Hi, guys. Thanks for joining in. My name is Paige Arthur, and I work at NASA's Jet Propulsion Laboratory, which is part of California Institute of Technology. And like Jesse said, I'm going to talk about the NASA's Psyche mission, which is a mission to an asteroid. A little bit introduction about myself. I started really enjoying space when I started watching Star Trek at 13. There's a picture of me on the right at Kennedy Space Center Star Trek exhibit in 2011. So then I asked myself, what could I do to get involved in space exploration? And while we're not exactly building starships like the Enterprise right now, I wanted to kind of do the next best thing. So I went and I studied aerospace engineering in Colorado. And then from there, I got a job at NASA at the facility called Jet Propulsion Laboratory, where they do a lot of the deep space missions. I'm sure all of you have probably heard of NASA before, but what you might not know is that there are different parts of NASA that do different things. So Kennedy Space Center in Florida does a lot of the launches. Johnson Space Center in Texas does the crewed missions. JPL does the autonomous deep space missions. So we send not humans, but robots out into deep space to figure out more about our solar system. This is just kind of a cool visual representation of all of the missions that JPL's done. You can see we've done a ton of them to Venus, to the moon, to Mars, to Jupiter. A lot of what we know about the solar system comes from JPL. And all of that information that we get down comes through this room or a similar one at the Jet Propulsion Laboratory, where we call this room the center of the universe, because all of the information that's coming from deep space to Earth has to come through this room here. So I'm going to give you a brief video to show you a little bit about how cool the Psyche mission is.
There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal rich.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
After launch, we cruise through interplanetary space for a number of years. First, we fly by Mars for gravity assist that'll slingshot us into the asteroid belt. And then we're thrusting all the way from there to finally arriving at Psyche.
We'll go into 4 orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma-ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
We're using a particular thruster technology, Hall effect thruster technology. They operate 5 times more efficiently than normal rockets, so they use a lot less fuel, and is what allows us to get into orbit around this asteroid.
Solar electric propulsion has been around for quite a while, and it has flown before, but we're continuing to push the boundaries. We're going to have big 5-panel fold-out solar panels that will provide the electricity for the thrusters, which use as propellant the noble gas xenon.
This will be the first time that Hall effect thrusters have flown in deep space.
Studying the evolution of a planetary body is a detective story.
There's a magic to when you actually are on the launch pad and you say, we'll go for launch.
And you feel like singing and dancing, and you feel like throwing up at the same time.
Let's go discover things about our solar system that we have no other way to do. I think that it's fundamental to who we are and also who we should be. It's an incredible opportunity to be a part of the team making that happen.
So that's the Psyche mission. That's what I've been working on for the last 6 years at JPL. And then this is a picture of what the spacecraft actually looks like that's on the mission right now. And it's currently in deep space trying to get from Earth to Mars and then from Mars to the asteroid. So I'm going to talk a little bit about how the spacecraft itself works. And the first big question is always, how are we going to power this thing? Because there's a lot of different components that need to function, and they all need to get their energy from somewhere. So the short answer is Psyche gets its power from the sun. And the way that it does that is with these huge solar arrays that the whole spacecraft, when you stretch it out with the solar arrays, is like the size of a tennis court. So it's really big. And we had to integrate these solar arrays with the chassis and do a test where we spread them out in the high bay. There was only room to do one at a time in the room because it wouldn't fit with both of them extended out at the same time. So once Psyche gets its energy from the sun, it stores it in one of its batteries, and then from there it can use it to power all of its components. The biggest, one of the most important ones is, how do we get from Psyche to the asteroid? Well, we use what we call our electric propulsion Hall thrusters. Now this is pretty cool because traditionally deep space spacecraft use chemical propulsion, kind of like a regular car. But Psyche is sort of the Tesla version of a spacecraft. It's not using traditional chemical propellant, but it's using electricity that it gets from the sun to power these Hall effect thrusters. You can see these pictures here. This is actually what these Hall effect thrusters look like to the naked eye. It's not an edited image. It's not infrared. This is actually what it looks like when the xenon ions come out of the Hall effect thrusters. The force that this exerts is very, very light. It's like the weight of a slice of bread. Imagine that is the only force that's pushing on that entire massive bus-sized spacecraft. So you might not think that that's enough force to move the spacecraft, but luckily for us, we're in outer space where there's no friction to get in the way. So even though it takes it a long time to accelerate, if we're thrusting for thousands of hours, it eventually builds up and we get going very, very, very fast. And the benefit of this is it's a lot more efficient. So we need a lot less fuel than if we were using traditional chemical propellant, but it does take quite a bit longer. So that's why it's taking us a full 6 years to get from Earth to the asteroid. When we loaded all of the xenon onto Psyche, when we were out doing our ATLO operations, we got to exactly 1,085 kilograms of xenon. So that picture on the top there with the balloons is when the propulsion team was excited that we finally finished loading all the xenon, and they brought us in balloons to commemorate the event. So once we're at the asteroid, what is Psyche going to do? A couple of things. It's going to use its gamma ray neutron spectrometer to determine the elemental composition, so figure out what it's made of, how much metal's down there, how much nickel versus iron versus other things that we might not even know about. It's going to use this fancy looking instrument here. It's also going to search for a magnetic field using its magnetometers. If it finds a magnetic field, then that's a pretty good indication that Psyche may have been the core of a protoplanet whose mantle got stripped away, which would be really interesting for geologists and planetary scientists to learn more about how our own metal core might have been formed. It's going to use its imagers to take pictures. It's going to take pictures of the whole surface of the asteroid so that we can map it out really accurately. And then it's also going to measure its gravity field. This is really important when it comes to flying the spacecraft, because if you can imagine a satellite going around Earth, Earth is pretty much a sphere. It's almost a perfect sphere. It's a little bit fatter around the middle because it's spinning and it's got some other perturbations, but it's pretty close to a sphere. Psyche, on the other hand, looks more like a lumpy potato, and that can be tricky when we're trying to fly around it and do maneuvers around it because we don't know which way the gravity is going to be pulling on Psyche at which parts in its orbit. Now, we don't have an instrument like the gamma ray neutron spectrometer or the magnetometer that can directly measure a body's magnetic field. So instead, what we do is we actually use our communication antenna to do this, which is the silver disc in the picture down at the bottom there. The reason that this works is that when we're communicating with Psyche from the ground, we get messages from our antenna, and with those messages, we know how far away the spacecraft is and how quickly it's moving. And so once we get a bunch of those data points, we can sort of map out what its path looks like while it's in orbit. Now you can imagine if it were orbiting a perfectly circular body like the Earth, its orbit would be fairly circular or elliptical. However, for a body like Psyche, it's not going to be very elliptical. It's going to be pretty irregular. So we can map that out and use that information and do some fancy math to figure out what Psyche looks like, what its density is, what its shape is. Psyche is also hosting a really cool engineering demonstration called the Deep Space Optical Communications, or DSOC. And this is essentially a space laser. So like I said, we're using our antenna to communicate with Earth, but at the same time, we were also demonstrating that we can talk to Earth, not with an antenna, but with light. And the reason that this is really cool is that we can fit a lot more information onto this beam of light than we could onto a radio antenna. So we're talking, we're able to use this information to communicate a lot more information quickly. And so when we were testing this after we launched, we sent a very important video back from Psyche to Earth to demonstrate that we could make this happen. So I'm going to play you guys that very important video.
Very important.
So that's Taters. I think he's a cat that belongs to one of the people on the DSOC team, and they decided that he was going to be the first video that we sent from deep space back to Earth via laser. And there was a lot of other kind of important information in the background of that video, but obviously the cat was the most important part. All right, so now I'm going to talk about how do we point the Psyche spacecraft. This is really important because if we got up there and we're orbiting the asteroid, we can't do much if we don't know how to point our antenna back to Earth or if we don't know how to point the cameras at the asteroid. So this is a really important job. The first question that we have to answer is, which direction are we pointing? Now, if you imagine, the first sensor that we have are our sun sensors. So if you imagine, if you close your eyes and you walk outside and it's a sunny day and you kind of turn around a bit, even with your eyes closed, you can probably still tell about where the sun is coming from because you can kind of sense that there's a more of a light intensity in one direction and maybe more dark in another direction. And that's exactly how our sun sensors work. They're not particularly precise. They're not going to be able to tell you what street corner you're on, but they'll be able to tell you whether you're facing the sun or not. And that's really important because the first thing that we always need to do when our spacecraft is up in space is make sure that our solar arrays are pointed to the sun so that we can have enough power to do the rest of the things that we need to do. Because if we run out of power, then we're just going to be kind of sitting dead in the water. Then we'd be in big trouble. The second sensor that we use to figure out which direction we're pointed is our inertial measurement unit. So imagine again that you're outside, but now you're sitting on a spinny office chair and your eyes are closed and somebody comes and starts to spin the office chair and you start rotating. Even with your eyes closed, even if the sun wasn't out, you could probably still tell that you were spinning because your vestibular system in your head is feeding you information where you can just kind of feel the motion. That's the same thing that an inertial measurement unit does on a satellite. The final thing now, imagine you're still sitting outside and you open your eyes and you can see the street intersection down the street. Now that's very similar to how our star trackers work. They do kind of just what it sounds like. They point to a section of the night sky and they recognize the star pattern there, and then they use that to figure out exactly where they are very precisely. So with that information, we know exactly which direction we're pointed. So once we figure out what direction we're pointed, the next question becomes, how do we get to where we need to go? We have two different, we call them actuators to get us there. The first are called cold gas thrusters. We've got 6 of these little thrusters at different points on the spacecraft, and they just release little bits of air out into the vacuum of space, like 6 little farts on the spacecraft, and we can use those to turn the spacecraft whichever direction we want to. But we don't want to use those too much because we only have a limited amount of air that we store on the spacecraft. So what we usually use are called reaction wheels. And these are some of my favorite parts of any spacecraft because they're very simple, but kind of not intuitive. And they use some really cool math to work. Specifically, they use a concept called conservation of angular momentum. And I'm going to show you a brief demonstration on how exactly conservation of angular momentum works on Earth.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Move back, and I stop. Flip it, I spin. So the question is, why am I spinning?
So the answer to that question is conservation of angular momentum. And it's not something that we experience firsthand on Earth so much because there's so much friction down here that kind of stops us from feeling the effect of it. You can only feel it when you're kind of doing what this guy's doing and standing on a low friction surface. But we're able to use this to our advantage on a spacecraft by putting on 3 or 4 essentially bicycle wheels like what that guy's holding. We call them reaction wheels, and they're a little bit more heavy duty and fancy than a bicycle wheel, but they really just work the same way that you were seeing this guy move. We were able to spin up these reaction wheels and the body of the spacecraft will actually spin around them. So once we've got the spacecraft all built and ready to go, the last part of any launch campaign is shipping off to Florida, to Kennedy Space Center, where we do our big launches. And that was our whole team got to be down there for a full 9 months, which was quite an adventure. The picture on the upper right is the spacecraft right before encapsulation, which is where we encapsulate the spacecraft into the launch vehicle, the rocket. So that's my team getting all excited that it's almost launch day. The picture on the top left are the SpaceX rockets after Psyche's been put on top of the rocket. The first time I walked into the SpaceX high bay and saw this in person, I must have looked like a cartoon character the way my jaw dropped open, because one of the SpaceX engineers walked in front of me and actually laughed at the expression on my face. I was just so awestruck by how incredibly huge this machine was. It was so cool to see something that you've worked on for 5 years being part of such an amazing campaign. And then the bottom left photo is the rocket standing up, and our spacecraft is up in that little cap in the top, all tucked away safe for launch. And then the rest of the pictures are us enjoying Florida and all it has to offer. And then we got to launch day, which was one of the most incredible days of my entire life. I will never forget it. I think I cried like 3 different times. I was just so proud and so relieved, and also a little bit sad to see our spacecraft going off into space where we would never see it again. But it was a really, really magical day. I was got to see it from the viewing center with the rest of the team, but then as soon as it launched, I ran as fast as I could and I drove as fast as I could back to the command center in time to see the live video feed come from the SpaceX rocket showing this.
Psyche payload separation confirmed.
There it is. The Psyche spacecraft going off into deep space, 2 billion mile journey.
That is an awesome shot to see Psyche leaving the stage 2.
So that was the last time that human eyes ever laid eyes on the spacecraft, which was kind of another emotional moment for everybody, seeing our baby go off into deep space. And then I stuck around and watched some of the telemetry come through from what we call initial acquisition, which is the first time that Psyche deploys its solar arrays and starts actually communicating to ground and giving us telemetry and saying like, hey guys, here I am, I'm safe, I'm unfolding my solar arrays, I'm pointing myself to the sun, I'm turning on all the different components that need to be turned on. So watching those messages come down in real life for the first time was also a really, really cool moment for everybody. But just because we launched doesn't mean that the work ends. So now, ever since last October, we've been figuring out how to fly the spacecraft. So we'll send up what we call sequences of commands, and those commands will do everything from telling it when to turn on and off those electric propulsion thrusters that we were talking about earlier, when to turn its antenna to Earth so that it can communicate all of its information, when to turn on the science instruments, all those kind of things. So we have to send that information up to the spacecraft every time that it passes over a deep space network pass. And then once we send up those commands, we get telemetry back from the spacecraft that tell us which direction are we pointed, which it figures out based on the readings it gets from those sun sensors, inertial measurement unit, and the star trackers. It tells us how quickly it's spinning. It tells us if all of its components are functioning properly or if anything's sick that somebody on the ground needs to go in and look at. It takes a full 30 minutes for our information to get from the ground up to the spacecraft, and then another 30 minutes for the information from the spacecraft to get back down to us. So that's a full hour that we have to wait after we send something to make sure that it got there. And that's, keep in mind, that's traveling at the speed of light, which is, the fastest. It's essentially the universe's speed limit. So as fast as you could possibly imagine. Even at that speed, Psyche is so far away from us already that it takes that long. You can see some pictures down below, or some of the shifts that we had when Psyche was in range of one of the deep space networks, and we were getting telemetry down. And we've got representatives from all of the different subsystems who are all experts in their respective fields, making sure everything's working. And then, of course, a selfie that I snuck of myself because it was pretty cool to be saying I was helping fly a spacecraft. So right now we are on our way to the asteroid belt. We've left Earth. We're going to do a flyby of Mars. The reason that we're going to do that is that we're actually going to steal a little bit of Mars's momentum in what we call a gravity assist. So we angle ourselves such that we fly close enough that we get into the gravity field, and then come at it at an angle that we end up stealing some of that momentum. So when we do this, Mars will actually slow down the teeniest fraction, but it's such a massive body that it probably won't notice. So don't worry, Mars will be fine, but we're going to steal just a little bit of their momentum to get us where we need to go. And that'll help slingshot us all the way into the asteroid belt, where we'll catch up with Psyche and then do another burn of our engines to get into orbit around it. Once we're in orbit around Psyche, we're going to start at a pretty wide orbit because we still don't know a whole lot about the asteroid. And then we're going to study it from pretty far away to figure out what its gravity field is. And that information will help us know what maneuvers we need to do to get in even closer. And so we'll get closer and closer to the asteroid and take more and more close-up science observations each time we do. So yeah, we'll get there in 2031, and then we'll start our orbital operations and start learning about the asteroid.
Super cool, Paige. Well, thank you so much for this deep dive into such a neat mission. And again, one we've never covered here in the history of exploring by the seat of your pants. What we're going to do to begin is have a little Kahoot to test some understanding for bragging rights for everybody. So if you want to help us out with any of these hints with the questions as we go into this, feel free to chime in when there's a few seconds to spare. But for you and for our audience who are new to this, the faster you answer, the more points you get. And what you win is Paige and I's everlasting respect. So please do get ready, get at the computer. And if you just want to yell out the answers in your class, that's totally fine as well. And then we are going to head to Mr. Hancock's class for the first question when we dive into Q&A. YouTubers, feel free to chime in as well. We'd love to hear from you in the chat. Mr. Kansas class, our Johnston crew, lots of folks all ready for when we go live with questions. But Paige, are you ready? We're going to dive in. Let's do it. All right. Okay. Journey to an asteroid. 3, 2, 1. All right. Question 1 for everybody. NASA's JPL is located where? This is the lead into the whole thing. Where are we? You said this at the very beginning of the broadcast, but I really want to harp on this because you mentioned that there are a lot of NASA centers, some places sort of classically associated with NASA. Does anyone know where the Jet Propulsion Laboratory is? Paige, what's the weather outside today there?
It's like 60 degrees and partly cloudy. It's usually sunny though.
It's snowing where I am in Newfoundland, so I'm very sad. But most of you got this right. California is correct. Pasadena, so Jet Propulsion Laboratory, not only do they get to work on the coolest things, but they get to be in like the happiest, best spot in the southwestern United States. So Soaring Buffalo has our lead. Let's go to question 2. Asteroids are made of what? Why are we going? What's the deal? Are they made of ice? Are they made of rock and metal? Are they made of star stuff, the same thing that like our sun is made of? Or do we have no idea? Maybe that's why we're going, is we have not even the foggiest clue what asteroids are made of. Paige, any hint we want to give our audience here?
Looks like we got it all right.
Everyone got it right. Wow. Sorry, that almost never happens in like 500 Kahoots. That's wild. You guys like were right on the ball with that one. So comets are made of ice. I'm not wrong. Sometimes there's some rock affiliated with them, but largely they're ice, and asteroids are rock and metal. That is sort of the differentiator that we give to people when we talk about them. Yes. Cool. All right. There's our lead. Oh, our lead changes. Decisive Iguana takes our lead. Question 3. The Psyche mission is exciting because of what? We had a cool video in the middle here. Is it because we're going to mine it for metals? We're going to get all some like platinum and other cool stuff from it? Is it because it's the closest we can get to study something like the core of a planet? Is it because we want to blow it up, which sounds kind of cool? Or is it because we want to sling it at Mars and like throw it like the asteroid impact that wiped out the dinosaurs? See, this is news to me, and most of our audience got this right. Like the idea that it's this possible core of a planetesimal in the past, and we have this opportunity to look at something that would be like the core of the Earth is very neat, because the core of our planet is this big hunk of metal, and we can't get down there. We can only study it indirectly. So to be able to fly by something and take samples and check it out and all this cool stuff is very, very neat. Paige, we're going to go into our final question, and then you are going to get ready for questions. Mr. Hancock's class first. Let's go to our final one, and then live a Q&A. Psyche gets its power, or not Psyche, the Psyche mission gets its power from nuclear energy, solar power, gasoline, or it doesn't need any power. What? Who needs power? What do we think? I love the little image you had of the xenon beam too. It's very neat.
Yeah, I got to see that in person when they were testing it in their lab, and it was really cool to see with my own eyes.
It's very it's like, I mean, it's literally and figuratively very spacey. Now, most of our audience got this right with solar power. Let's see what that does to our leaderboard. YouTubers, feel free to chime in with questions, and then we're diving in. But Dr. Koala is third. Second is Soaring Buffalo. And first, for all the marbles, is, by 7 points, Decisive Iguana. If you are any of these folks, let us know who you are in the chat. And Paige, we're going to dive in with questions. So Georgetown, Mr. Hancock's class, if you guys want to lead us off with a question, you are good to go. Hey, man. Win.
Oh, hey, Jesse. How's it going? Just talking to my class. We had a question. A couple of students originally were wondering when it's going to come back, but you said it wasn't coming back. Like, what's the plan for afterwards?
Yeah, that's right. Psyche's actually not going to come back because we would have to put on a lot more propellant than we have room for right now. So it's just going to stay orbiting the asteroid. Once we finish our primary mission, we might apply to do a secondary mission and see if NASA wants to continue to fund us for operations. If not, then we probably will stay in orbit around the asteroid. We won't need any won't need to do any operations to it should just naturally continue to orbit it, unless they decide they want to do some kind of disposal burn like they did. If you're familiar with the Cassini mission, they actually drove it into Saturn's atmosphere where it burned up and disintegrated because they didn't want it to potentially hit something and contaminate another planetary bodies, or like Titan, one of Saturn's moons. So they actually purposefully destroyed it. So I hope they don't do that to Psyche, but they might decide that they have to. But yeah, that it's not going to come back. It's just going to send us information from where it's at in orbit.
I'm really glad we got this question because I think this is a misconception a lot of people have, not just kids, but everybody. Most missions don't come back to Earth. In fact, we're planning a mission to Mars, the Mars Sample Return mission, which is like decades in the making. That is going to be this rare thing that's going to go and pick something up and bring it back. But most things just go off and stay out there forever or endlessly keep leaving past the Earth, like the Voyager mission. So very cool. Thank you, Paige. All right, Irving, Texas, Mr. Kansas class, come on in and you're good. You're good. Hey.
Are you nervous if it crashes in the neutron belt to something?
I'm not too nervous. I think the people at JPL are really, really good at doing math to make sure that that's not going to happen. I think another common misconception is how dense the asteroid belt is, because when you see it in movies like Star Wars, you see these rocket ships like trying to dart through the asteroid belt and trying to avoid collisions. But in reality, the asteroids are really, really spread out. So it's really unlikely that Psyche's going to encounter anything else in its path on its way there. And even if it did, we would be able to tell when that was going to happen and fire the thrusters to maneuver around those different things. So I'm not too worried about it.
This is actually a really good point. I was going to have this in the Kahoot, so I'm so glad you asked this, because this is the big conception. And you mentioned Star Wars, like the perfect example. You're in the Millennium Falcon, you're like deking all the asteroids. Not even remotely like that, to my knowledge, and you can correct me if I'm wrong. We don't even when we're creating the trajectory to send something past the asteroid belt, we're not conceiving of it hitting an asteroid. We're not worrying about each individual rock because they're so far apart that it would be literally astronomically unlikely that you were to hit something, right?
Yep, that's correct.
Cool. All right. So thanks for the question, Mr. Kansas class. All right, we're going to head to Mr. Johnson's class. Unmute your mic and come on in. Take us away. Hey.
Hi. So this question was for Paige specifically. I had some students wondering what your kind of grades and classes were like in high school to get to where you are now.
I think I had like a 3.8 GPA in high school, unweighted. Definitely was prioritizing the science and math classes to get to where I'm at, though English is definitely also important to study so that you know how to communicate your ideas well. There are a lot of engineers that I work with who are absolutely brilliant, but don't always know how to communicate their ideas quite super clearly. So I think it's all pretty important.
I'm so glad you asked that question. We're willing to ask that. Thank you for answering, Paige. We have a lot of NASA people on. We have a lot of scientists and explorers of all kinds. And I would say that overwhelmingly, most people are pretty good at school. They take school seriously. They try to learn new things, even if they struggle in some subject, that they work on that and get it better. And particularly for a job like Paige's, you need science and math ultimately. But we've had a lot of people that completely failed too. Like they literally failed math, failed science in high school, retried it in university. We had a space junk expert on last week who did failed things in high school, went back to college as an adult, and now gets to work on cleaning up space junk in the solar system. So really, whatever you're interested in, keep plugging at it. And if you're lucky enough to be really successful early on in 15, 16, 17 and get to somewhere like Paige, great. But if you're not, there's lots of opportunities for you too. So thank you so much for that question. That was great. YouTubers, please do chime in. Feel free to put your questions in the chat. We're going to go back for another live round of questions while we're waiting. So Mr. Hancock's class, come on back in and take us away.
Paige, there was that one graphic you showed about the flight plan, and a couple of students were wondering why you don't just fly directly to Psyche and you're just doing these loop-de-loops.
That's a really, really good question. The truth is, it would take a whole lot more energy to go in a straight line from Earth to Mars or from Earth to Psyche. And that's because so if you think about Earth and Mars and Psyche, they're all orbiting the sun. The sun exerts a very strong gravitational field on all of the planets in its solar system. And that's why we stay in the solar system. We don't go shooting off in a straight line. So we want to take advantage of those orbital mechanics when we're designing our trajectory so that we can use the fact that we are already, as soon as we launch, we're in orbit around the sun because we're coming from Earth, which is in orbit around the sun. So we want to stay in orbit around the sun to get to where we want to go, because then we don't have to use our own energy to maneuver around the solar system. All we have to do is increase or decrease the radius of our orbit around the sun, which is a lot easier than getting out of the sun's orbit altogether. I think if you were to compute the escape velocity of the sun, it would be something absolutely astronomical. So we want to stay in orbit around the sun, and that means going in those loop-de-loop patterns.
It's really hard to visualize this. We talked about Europa Clipper earlier this month as well, and its flight path looks insane. Like you'd never, if you were to conceive of it as an amateur, you would never come up with what was come up with for that. I guess the closest analogy of thinking about it is if you had a carousel spinning around and you wanted to get to somewhere on the other side of it, you would run up and grab the edge of that, and the power of that would swing you and fling you a little bit faster that way. It's like the closest analogy we have here on Earth, but when you get into orbital dynamics, it's pretty complicated and a really, really cool question. You guys have some great questions so far. Thank you so much. All right, Mr. Kansas class, we're back with you guys. Come on in and take us away. Take us away.
How hot is the asteroid of metal?
Ooh.
How hot is it? I don't know for sure in degrees, but because it doesn't have an atmosphere, it's probably going to be really hot where the sun's hitting, like hotter than anywhere on Earth, but really, really cold in the shade. So that's kind of the interesting thing that you don't think about is on Earth, because we have our atmosphere, it kind of keeps everything at a relatively constant temperature, whether it's night or day. Obviously, it's colder at night when the sun goes down and a little bit warmer in the day, but we still stay within about the same survivable temperature range. But because there is no atmosphere up in space, when the sun is hitting something, it's hitting it with all of its force and making it really, really hot. And when there's shade, you don't get any of the sun's energy, so it's really, really cold.
I love this question. So on the moon, there's a great example. That's you have all experienced this. You're outside, it's daytime, the sun goes down, night falls, and it gets a little bit colder, or it gets quite a bit colder depending on where you are. On the moon, if you walk from like shadow to sun, it's like some crazy thing, like it's several hundred degrees difference because of everything that Paige just mentioned. So that is such a cool question. I'm surprised to hear that even as far out as an asteroid, you'd have that much of an impact with the sun where it would be super hot, but that's really fascinating. So thank you for that too. Great question, guys. Mr. Johnson's class, if you guys have a second one for us, feel free to unmute, flick on your camera, and come on back in. Time flies when you're having fun, so we are nearing the end of the broadcast. I'm going to highlight again, if you want to check out the Psyche mission, there's some great websites for this, jpl.nasa.gov, so more to keep the learning going. And this program, like all our others, will be on our YouTube channel, so there's more to explore when you're there. If you guys don't have a question in Mr. Johnson's class, that's totally fine. What we'll do is we'll wrap up with one more from Mr. Hancock and one more from Mr. Kansas class, and then we'll say goodbye to everybody. So come on back in Georgetown. Hey, guys.
Hey, Paige, one of our students was wondering, like, what's a typical day like for you from beginning to end?
These days, I'm doing a lot of the planning for how we are going to fly the spacecraft once it gets to the asteroid. My particular job is about how to get between the different science orbits. So if you remember from one of the slides I showed, we had 4 different science orbits. One of them was sort of rotated kind of funny, and it's really, really difficult to get from one orbit to another when there's that, we call it an inclination change. So it's not just getting bigger or smaller, it's actually changing the way that it's inclined. And so there's a lot of math that has to go into that. And we need to be able to make sure that the spacecraft can turn the thrusters fast enough to be able to get the thrust vectors that we need to get between the 2 orbits. So my job right now is running simulations to make sure that it can do that under a wide variety of scenarios. So obviously, since we can't test this in space right now, since we're not at the asteroid, we've got a bunch of software that's pretending to be the system and pretending to be outer space. It's kind of like playing a video game, but not quite with all the pretty graphics. But I'm plugging in a bunch of numbers and saying like, oh, if our mass is this much, then what would happen if this happened?
I love the day-by-day question. We get this almost every time, so thank you for this. It's always neat to learn about new careers in this way. Paige, time flies and you're having fun. We're going to take one more question from our audience before saying farewell. But again, guys, check out that NASA Psyche site. I'll email it to all our registered classes to keep the learning going. And with that, Mr. Kansas class, if you guys want to come in for one final query, you're good to go. You're good to go. Oh, Mr. Kansas.
How long did it take?
Repeat that one more time.
Yeah, how long did it take to build the spacecraft? Is what you want
Nice.
To build it?
Yep.
It's been in the works for, I think, over a decade was when the first proposal was written. It was built, it's kind of a hard question to answer because all of the components were built very separately. But we started what we call the ATLO campaign, the assembly, test, launch, and operations, which is the final stage of everything kind of getting plugged in together and making sure everything works together. That probably took 3 years for all of the dispersed parts to come and be built up into a single system.
Thank you so much. I love that we get to highlight these things about how long missions take, because it's way longer than people think. And so when you're someone like Paige, you get to work on a project for 3, 5, 10 years sometimes. It sounds so outlandish. But at the end of that, you get a mission that goes off to explore other worlds in the solar system. And it's one of the coolest things that you can possibly do as a scientist, engineer, or researcher in the world, ironically. Thank you guys for wrapping up with this. And Paige, before we say farewell to our audience, is there any last message you want to leave our kids with today?
I kind of wanted to return for a sec for what you were saying about the question about how I did in school when I was that age. And I kind of wanted to stress that, like, I work with engineers who went to MIT and Caltech, but I myself just went to University of Colorado Boulder, a state school. And I don't feel like I'm, kind of missed out on it. Like, I feel like I'm very much on par with all of my coworkers who went to, the fancier technical schools. So if that is your path, then that's great. But if it's not your path, then there's a bunch of different ways to get to where you want to go.
I'm so happy that you shared that. And again, we don't get that question very often. So Mr. Johnson's class, thank you so much for sharing that. I think it's really important for all our kids to hear. And truly, like, we've had 3,500 plus broadcasts over the 10 years we've been doing this, and the career paths there's 3,500 different career paths to get there. So whatever you're interested in, keep plugging at it, learn, volunteer, get involved with cool organizations. If you get the chance to work at somewhere like NASA JPL, lucky you, and pinch yourself daily. But really, really special to get the chance to share all this. So Paige, thank you so much for joining us. And what we do to wrap up every broadcast, I'm going to bring in all our kids to say thank you and farewell. So Mr. Hancock's class, Mr. Kansas class, Mr. Johnson's class, thank you so much, everybody.
Later.
And bye.